Welcome back. We are looking at the transport of the various physical quantities when there are simultaneous presence of more than one driving force. This is the last chapter of this course, and we have already looked at the mass flux in the presence of a concentration gradient and an electrical potential gradient being present at the same time. And we saw various different applications of it. We also saw that it is the basis for us to perceive our world through our senses, as well as to act based on the directions given by the brain and so on and so forth, as well as it is the electrophoresis, as well as the industrial equivalent of that can be understood, analyzed, and used for design using this principle. Let us take things further today. Today we'd look at simultaneous concentration gradient and velocity gradient. Earlier it was concentration gradient and electrical potential gradient. Today we are going to look at simultaneous concentration gradient and velocity gradient. Let us again pose a problem of definite importance to us, especially in these COVID-19 times, when one of the difficulties that is caused by the virus seems to be the stripping away of heme from the hemoglobin, or it seems to destabilize hemoglobin, and that seems to cause a lot of difficulties. When people go through that, one of the things that can be done is to oxygenate the blood after making sure that it has enough appropriate hemoglobin and so on and so forth. Not just in this situation, in many different situations, blood oxygenator, where the blood is taken out of the body and a device is used to oxygenate the blood, that becomes essential, especially during open heart surgeries and so on and so forth. That becomes essential. This is the basis of the heart-lung machine, or one of the important aspects of the heart-lung machine, and so on. So it has wide applications, and that is based on, or in other words, in the blood oxygenator, at least in the oxygenation part of it, you will find the simultaneous interplay or simultaneous presence of the concentration gradient and the velocity gradient. Let me read the problem and then present this situation as a solution to this problem. Blood oxygenators are extensively used in hospitals when blood is taken out of the patient during surgical procedures or otherwise, like now, to be returned later to the patient. In a type of blood oxygenator, the falling film type, that is, a blood film flows downward on a solid wall. Okay, this is the wall that is given here. This is the blood that is flowing. This is the blood film here, a thin blood film. I've just blown it up here for understanding purposes. It's a thin blood film that flows over a vertical wall, while oxygen diffuses across the film and oxygenates the blood. Okay, it interacts with hemoglobin, and thereby the hemoglobin gets its capacity of 4 oxygen molecules, and each hemoglobin molecule gets its capacity of 4 oxygen molecules ultimately, and that is what happens to oxygenate the blood. Let us analyze the situation to derive an expression for the rate of oxygen absorption into the blood film. As you realize, the rate of oxygen absorption is a key design parameter. You need to know whether you are able to restore the oxygen level in the blood to the previous levels, or to the levels that are needed just by a simple pass through the oxygenator. So that is the crux of the design of the oxygenator, and therefore we are looking at that in this particular problem. So here, as I mentioned earlier, you have a simultaneous velocity gradient. You know, this is a film that is falling over a flat plate. Earlier we saw an inclined plane. Now the plane is vertical. the only angle difference here pretty much in terms of the flow. Otherwise, the flow is a thin film that is flowing, thin film of liquid, in this case blood, that is flowing. And we saw that there was a velocity gradient here in the film. The velocity closest to in the layer closest to the wall will be 0, and in the layer that faces the air, here it's air, oxygen is diffusing from the air. The layer that faces the air, it will be the maximum that we have already seen. And that, so you have a velocity gradient in the x direction. X is this here, and z also there are quite a few things that come about. So you have simultaneous a velocity gradient as well as a concentration gradient here. Let us take the equations approach. Just to show you, I'm going to make a point at the end as to some of the limitations we might face with this approach, and therefore let me take an equations approach to this. The continuity equation that we derived and used earlier is capable of handling simultaneous concentration gradient and velocity gradient. Okay, this is the way it was derived. Why? Because we were trying to develop some standard means by which we could look at these systems of relevance, and these systems of relevance have velocities in them, and therefore we considered a cuboidal control volume in a rectangular Cartesian coordinate system where there were flows in all directions. It's a three-dimensional flow which can be looked at through its components in the x direction, y x direction, y direction, and the z direction. Okay, they were components of the flow. The flow is a vector, it's a three-dimensional vector. So the components are in the three different directions, and so on and so forth. So so we had used that framework to derive the continuity equation. Okay, so that was to make things a lot more complete in the terms of our approach. If you recall, we had used pretty much the same approach across the various conserved quantities, deriving the conservation equation for those conserved quantities, the equation of continuity for mass, the equation of motion for momentum, the equation of thermal energy using energy, and the equation of charge conservation. Okay, so pretty much the same framework was used. Only thing is, therefore, we needed to use that framework. Our approach here was to look at primary driving forces first. So that I felt was much better in terms of understanding. When we looked at the primary driving force for mass flux, then the velocity related term, the convective term, became a different driving force altogether. Okay, and therefore we said that we will not consider that at all. The equation had all that. Let me show that to you here. If you look at the continuity equation, this was the continuity equation here, and we had this term always in the continuity equation because of the way we derived it. Vx, Vy, Vz were set to 0 when we looked at mass flux due to diffusion alone. Okay, so that was kind of deliberately done so that our understanding becomes a little better. Fine. So now we have both these in a generic situation where there is fluid flow. You'll certainly have Vx, Vy, Vz. Recall that Vx, Vy, Vz are the components of the fluid velocity. Okay, so that is, this equation itself can handle it. We don't need any other improved equation here. And usually the rate of oxygen transport in the vertical direction, this is z direction, due to bulk flow, there's a Vz, right, due to bulk flow, is much higher compared to the diffusion in the same direction. Okay, diffusion, I mean, it's again, diffuser flux is a vector, so it can occur in the x direction, y direction, and the z direction. So hold on, this is x cross y, so y is going into the screen here. So x cross y equals z, so that is consistent with the right-handed coordinate system. So we have the x, we have the diffusion, the axial diffusion in the z direction also. Nothing prevents that from happening. Okay. However, that is given by this term here, dou squared ci dou z squared, is the one that accounts for axial, in the axis direction, diffusion. Okay. However, we have all these. We are trying to simplify this, so let us see how to simplify this. This is the complete equation. Of course, this is for a Newtonian flow with constant C di or rho di, whichever you want to put it. And so let us see how to simplify this equation. Because the axial diffusion, the diffusion in the z direction, is much less, the flux due to that is much less than the flux due to the velocity in the z direction, the convective flux in the z direction. We can ignore this term when it is considered in combination with this term. This term is the one that corresponds to the convection, transport, and this term is the one that corresponds to the diffusion transport, both in the z direction. And since they are added together, when they are added together, if this is going to be much smaller compared to this, we can ignore this, right? It's the same as saying, the example that I gave you earlier. If one value is 1,000, the other value is a 1, whether you have 1,001 as a total value, or whether you have 1,000, which is very close to 1,001, it doesn't make a difference. Okay, so that's the argument here. We can ignore this term when it is added on to this term. However, in the x direction, into the blood film, there is no convective transport, right? There is, of course, there's no velocity in this direction. There is no convective velocity. Fluid is not moving in this direction at all. It is moving only in this direction. There is no convective transport, and only diffusive transport happens. Okay, so this term is certainly relevant. So if you simplify the equation, if we look at steady state, ignore the reaction term. For now, let us ignore the reaction term. We'll come back to this at the end. By assuming the reaction between oxygen and hemoglobin to be negligible for the time being, okay, sometimes these things are done to simplify, and then you'll have to evaluate it. I'll spend a lot more time on that later. If this A2 from table 2.3.2-1 for continuity equation at steady state, okay. At steady state, the first term goes to 0. The time derivatives are set to 0, so the first term goes to 0. There is no Vx, there is no x component of the fluid velocity. There is, of course, no Vy, there is no motion in this direction. There is only Vz, but Vz, of course, remains. That's much greater than this also. So this remains. There is no diffusion in, there is, this term, of course, is there because there is diffusion in the x direction. This is the x direction. So this stays. There is no diffusion in the y direction, and this term we have ignored in comparison with this term. Okay, and of course this is set to 0. So when you put all these things together, the only terms that remain are this Vz dou Ci dou Z equals, instead of di, I am calling it d effective, because this is through a film, which is different, may not be intrinsic diffusivity values that you find in tables and so on. So a d effective, which could be close to that, times d squared Ca is hemoglobin dx squared. Okay, so this is what becomes the governing equation that we got by applying material balance to this situation, okay, or applying the equation of continuity to this equation. So equation of continuity brings with it a strong base that we can use with confidence, and therefore when we apply it to a situation, we can take it to be valid without any further thought, and that has given us this particular thing. See, the confidence that we gain in this approach is immeasurable. Okay, that's the reason why we look at this. There are other downsides to it, which I'll come to in a little bit. Let us call this equation 6.2-1. Of course, we need boundary conditions to solve this. This is, this is the second order here, and you have first order term with Z here, and so on. So boundary conditions are at x equals 0, Ca equals Cai, the concentration at the gas liquid interface. Remember, the x is going from the edge of the film that faces the air inside. Therefore, x equals 0 is the gas liquid interface. So this Cai is the oxygen concentration at the gas liquid interface. Equation 6.2-2. The other boundary condition is at x equals 0, dou Ca dou x equals 0. At the wall, where in other words x equals delta the thickness of the film, oxygen cannot penetrate the wall, right? So if it cannot penetrate the wall, for a physical reality to occur, the concentration profile there needs to go through a maxima or a minima. Okay, that's the only way it can happen, and therefore dou Ca dou x is set to be 0. If this is there, then this condition will not be valid. Oxygen cannot penetrate the wall, cannot be represented. Therefore, this is set to 0. 6.2-3. And for the z coordinate, at z equals 0 at the top, Ca equals Ca0, the concentration in the deoxygenated blood that is entering this region at the top of the plate. Okay. As it flows like this and then drops. Our point of analysis start is at the top of that place where it gets oxygenated, and that is what we call as z equals 0. Ca equals Ca0, the oxygen concentration in the deoxygenated blood entering the top of the plate. Equation 6.2-4. Let us consider a thin film that is uniform. That's a good assumption. Then the situation is comparable with the flow over an inclined surface. You recall the situation in the momentum balance chapter, momentum flux chapter. Bostwick viscometer, that's the first big example that we considered. In fact, we looked at it using shell balances, and then we applied the equation of motion to show that equation of motion gives the answer in one step, right? So that was the Bostwick viscometer. And so in comparison with that, can go back and compare. Vz is not a function of z. Okay, we are looking at the region where the flow is well developed. Okay, so the top point may not be the entry directly into the thing, so there might be some distance there where there are entrance effects. So somewhere in the middle where the flow has stabilized, okay, the flow is well developed now, so that you can use this condition. Vz is not a function of z. Vz does not depend with z. Of course, it depends with x. In other words, at a particular x, Vz is the same at all z. And let us call it equal to V0. Now we prefer to work with non-dimensional variables. It makes our solution general. That we have already seen examples, many examples so far. So we'll do the same here. Let us define a certain theta as a function of eta and phi as Cai minus Ca. Ca, of course, is a function of x and z, divided by Cai minus Ca naught. Equation 6.2-5. Our eta is the x coordinate dimensionless variable, obviously x by the thickness of the film delta. Equation 6.2-6. And a phi, or a phi, whatever you want to call it, is equal to z d effective V naught divided by V naught delta square. Okay. This is equation 6.2-7. In terms of the non-dimensional variables, the differential equation and the boundary conditions can be written as, I'd like you to pause the video here, go back, substitute these, do the various derivatives and so on and so forth. Substitute these into the differential equation that we had earlier, which was this, and the boundary conditions, which are these, the differential equation, which was this, and the boundary conditions, which are these, and come up and transform the equations and the boundary conditions into non-dimensional variables. Okay. Please do this. This is one of the exercises that we do. Take some time, whatever time you want, that's perfectly fine. Time doesn't matter. So pause the video here, okay, and then after you complete that, unpause and then check whether you got the right answer. Go ahead, please. Okay, I wish all of you got this. The differential equation would have become dou theta by dou phi equals dou squared theta by dou eta squared. A nice, beautiful form. 6.2-8. And the boundary conditions would be at eta equals 0, theta equals 0, 6.2-9, at eta equals 1, dou phi dou xi equals 0. I think this is dou phi dou eta equals 0, 6.2-10, let me correct it. And at phi equals 0, theta equals 1. Okay. So this has to be, let me correct it right away. This is dou phi, there is no xi here, that's phi here. So this needs to be corrected. In terms of the variables that were used, and this was dou Ca dou x, therefore that is, we had, so this has to be an eta. We got it. Okay, so now let's get back to where we are. Okay, fine. So this is what we have here. Okay. If we use the separation of variables method, you need to go back to your math course and pick it up. Let me again remind you that this is not a course in math, and therefore any of these involved aspects you need to go back to your, if you're unclear about it, you need to go back to your math course. I'll give you some basic things so that the flow in going from one step to another is not broken. But this calls for a certain elaborate manipulation, and therefore you need to go back and check. Theta of, which is a function of eta and phi, is written as two functions, one as a function of eta alone, the other one as a function of phi alone. This is the basis for our separation of methods, separation of variables method, equation 6.2-12. And if we had seen this when we looked at the case of unsteady flow. Okay, recall flow in a pipe, in a cylindrical pipe, that is set into flow at time t equals 0, and then we were looking at the unsteady state region or unsteady state initial times before which it becomes it attains steady state. So that same, if you go back to the solution would be similar, the procedure would be similar. If you do that, this y could be a exponential of minus b squared phi, equation 6.2-13, and x, which is a function of eta, is b1 sine b eta plus b2 cos b eta, equation 6.2-14, and this you must know from your math course, which is a prerequisite for this course. So if you do this, and even if you don't know, doesn't matter, you can go and pick it up now. That's all. It doesn't really matter. You just need to spend a little more time in picking up these things if you have either forgotten or you haven't internalized these aspects in the course, the previous course. Okay, using the boundary condition 1, the cosine term would go to 0, and using the boundary condition 2, we get b equals n minus half by pi. Please try this out. Okay, I'm just presenting the solution to you quickly here. It's an involved solution. And when n equals 0, plus or minus 1, plus or minus 2, and so on and so forth, for b1 to be non-zero, otherwise you just get a trivial solution, this condition needs to be valid. Okay. Now you need to know something about the orthogonality of functions. This again you need to pick up from your math course. Let me very briefly tell you what that is to juggle your memory and then set you back to your math course. Two functions fm of x and fn of x are said to be orthogonal over an interval ab if integral from a to b, these are the limits of the interval, fmx times fnx dx equals 0. So the product of those two functions, you integrate them over this interval a to b, then that has to be equal to 0. That is when two functions are said to be orthogonal. So you look at the properties, the orthogonality property of the functions, and then here an example is given, integral of 0 to 1 sine m pi x times sine n pi x dx equals 0 when m is not equal to n, or when m equals n equals 0. But when m equals n but not equal to 0, also this is the case. And using the orthogonality relationship, we get the solution as theta of eta and phi equals 4 by pi sum of n equals 1 to infinity 1 by 2n minus 1 sine of n minus half pi n exponential of minus n minus half squared pi squared phi. Okay. Whatever I have presented you in the last two slides would take you quite a bit of time to work out. Okay, don't underestimate that. It's just that it is not an inherent aspect of the course. I have not gone into every single step of that, but this will give you a solution. And I'm also trying to make a point here. Okay, this is a solution. I presented you the solution. The main point that I'm going to make from the physicality of the various things is going to come up next. Okay, again, the complexity in math is not the focus of this course. Okay. Equation 6.2-15. Now let us take the height of the film to be h and b to be the wall width in this direction. The rate of oxygen absorbed, this is what we wanted to find out. WA in terms of the regular dimensionless variables would turn out to be this, right? I mean, this is straightforward. You have the flux here and you have the variation with respect to the area in this direction. Therefore, you need to integrate it from 0 to h dz and 0 to b dy. That would give you the rate of absorption of the flux. And the flux is the diffusive flux in this case, in the x direction, and therefore the fixed first law would give you the expression for JAX star. And if you put in that, WA will turn out to be, after a long set of manipulations, 8BL VZ CAI minus CA naught by pi squared, sum over n equals 1 to infinity, 1 minus 2n minus 1 squared, 1 minus exponential of minus n minus half squared pi squared h d effective V naught delta squared. Okay, there are various nestings here. Be a little careful of the nestings. Fine. This is equation 6.2-17. Good. So we got a solution. We had a representation of the situation here, the physical situation of the blood oxygenator. We wrote a model for it, a mathematical model for it. We had made some assumptions as a part of the model. Okay, these are very standard aspects of model development for various different things: analysis, design, operation. Okay. However, let us discuss this. This is also a part of the model development process. We have developed a model. Sometimes a model fits the data very well, and therefore we say our representation of the various important aspects of the model has been well carried out in a mathematical sense. Okay, or in other words, the model is a good enough representation of the actual system. It captures the essential features of the actual system. That's the purpose of the model at any time. However, here if you see, before that, the average oxygen concentration, if you derive an expression, it will turn out to be this. I'll let you read this. CA average would turn out to be this. Okay, 6 to 18. The model here, the oxygen absorption rate, whatever you get out of this model, it falls short in agreement with experimental data. So you have a model, you always need to go back and check with experiment, because you have made assumptions and hoped that you have picked up the essential features or the most important features of the process in your model. You need to check whether you've actually done that, and the only way to check it is compare it with experiments. Therefore, the checking is an inherent aspect of any mathematical model development. So in this case, it was found that the model falls short in agreement with experimental data. This they found out later was because the reaction between oxygen and hemoglobin has not been considered, because it's every molecule of hemoglobin takes in 4 molecules of oxygen when it is saturated. Okay, so that reaction aspect has been neglected in this model, and also the blood has been approximated as a Newtonian fluid. Right, that is the basis for us to choose the second equation, the easier equation to work with. So both these have turned out to be important, maybe, or one of these has turned out to be important. We don't know at this stage. So what is normally done is, if you need to take this route, then you go back, improve your model, then see, then compare it with experimental data, see whether it captures the experimental data well. Okay. And of course, the implicit assumption is that an experienced person has done the experiments. It is there's a whole lot of things to do on the experimental side to ensure that the data that has been obtained is indeed reliable. That's a totally different aspect of it. So this essentially happens in any model development process, mathematical model development process. Okay. So I think we need to stop here. Yes, yeah, we have completed this part. We will stop here. We'll close the lecture here, this lecture. And then when we meet in the next class, we can take things forward. See you then.